Hi, ladies and gentlemen. In the last class, we understood the concept of an event. What do you mean by experiment? What do you mean by sample space? And in the end, you understood that experiment is a trio containing omega, f, and p. Omega is a sample space, f is a Borel field, and p is the probability function assigned over that. So in this video, I will tell you about joint events. You understood that event in the last classes. You understood that the event is a subset of a sample space. Now we will see what is a joint event, what are independent events, and finally we will go into a very important theorem, that is a Bayes theorem and conditional probability. So let me start with that presentation. So this speech is organized into your learning outcomes, then joint events and independent events. Then we will see the conditional probability and Bayes theorem and the meaning of some terms. Then the summary of understanding. So what you will learn, or you will review joint events and independent events. And then you will observe some demos of joint and independent events. I will show you some Python codes. Then you will learn conditional probability, and you will learn Bayes theorem. It is a very deep theorem. It is a theorem of great consequences, great impact. And you will specifically you will learn the terms like the posterior probability, the prior, and the likelihood functions. So these are your learning outcomes. Then joint events means two things occurring simultaneously, or the intersection. If you put in terms of the set theory, the intersection of two events is called joint event. You know that an event is a subset of the sample space. So if these subsets have an intersection, if two events, that means two subsets of the sample space, they have an intersection, then that event is called a joint event. So you can think about a Venn diagram in which you have a common region or an intersecting region, that is called a joint event. Suppose let us consider a 6-faced dice, and let us consider two events, that is the outcomes are greater than 3, the outcomes are even. You don't have to have two dice, you can have a single die in which you can have one event as a greater than 3 and outcomes are even. These are all simultaneous events, or what you call the joint events. So these two coming together is a joint event. So marginal probability of getting an even output is 3 by 6, that is 1 by 2 in a row, and then the marginal probability of getting an output greater than 3 means it is 4, 5, 6, so it is 3 by 3, 3 by 6, that is 1 by 2. So the favorable outcomes for the joint event are for this joint event to happen, both dice can show either 4, 4, 4, 4. So one die showing 4, the other die showing 4, then the first the other way around, and then 4, 6, 6, 4. These things can happen. These are the outcomes. So the probability of both becomes both outcomes to be even and greater than 3, that is P A comma B. Often in set theory practice you usually use P A intersection B, but for most of our things we just write P A comma B. That shows that the probability of the joint event, okay, that is equal to 1 by 9. So I will show you a demo of this with Python codes. So here I have these Python codes. Let me see which one is that. I have a joint toss experiment here. See here, I import my NumPy. I open a Python terminal here. Open a terminal. I write IPython 3. I use Python 3. Okay. So this is my console. And here, if you look into this code, I import a NumPy module, or the numerical Python module, as say NP. Then I select some tosses, say I will keep it at say 1000 for simplicity. Then I toss two dice this way, like if I want to toss a die, what I can do is I can use the function np.random.randind. 1, 7 means this gives you the integers from random integers from 1 to 6. 7 is excluded. 1 to 6 with a size n. That means this x will be an array of 1000 values. Each value will be a random number between 1 and 6. Okay, and here also this is a second die. I throw another die, that is random dot random 1 comma 7 comma size equal to n. So as in the first primitive code I show in the first class, in the last class, I don't have to append things etc. Instead I can put it as a vector. This is one advantage of Python programming. You can do vectorized computing. So then what I do is I have to compute 3 probabilities. So I need to add something and then divide by the total number. So here some values, 3 some values I initiate to 0. Then I for I in range 0 comma n, for these 1000 tosses, I consider some event. So one event is this, that is if xi is greater than 3 and yi greater than 3. Simultaneously, if both these outputs should be greater than 3, and these are logical AND operations, so all conditions should be met. And np.mode is a modulo arithmetic operation, mode y. That means if y equal to yi is an even number, then this will be 0. And here also I am testing whether my outcome is even or not. So mode something comma 2 gives you, if that is equal to 0, then the number is even. So if this is true, then outsum 1 is equal to outsum 1 plus 1. So this is my joint event. With this if condition, I create my joint event. So if this joint event is satisfied, then outsum 1 is incremented by 1. Here I am trying to compute the marginal probabilities for this xi to be greater than 3 or even. So if xi is greater than 3, some outsum 2, another sum I have here, that is incremented by 1. Likewise, if this xi is even, like np.mode xi comma 2, if this xi is even, then out3 is outsum 3 is equal to outsum 3 plus 1. Then I compute these probabilities, outsum 1 by n, outsum 2 by n, then outsum 3 by n. So this should be the values we computed. So print these values, like probability of joint event is REPR is the whatever value of P1 is coming here, that will be printed here. That is the meaning of REPR. So I'll give you some separate sessions on Python programming. So until then you please follow these simple codes. So here I will write run join toss I have another t ss.py. Now you can see that probability of the joint event is 0.092, this is 0.5, and this is 0.512. Okay, you can now I can run this code for more iterations, like more die throwing. So you can compute this to be okay. Now it is instead of 0.092, I am getting 0.1122, which is very close to 1 by 9. Here you can see that 1 by 9 is 0.11, etc. Okay, this is each is 0.5. It is getting closer to 0.5. I'll add one more 0. Let us see whether my system stands that. Hopefully it will stand. Here you can see that it's 0.11 something. It is 1 by 9. This is 1 by 2, and this is 1 by 2. This is joint event, joint probability. These are marginal probabilities. So let me go back to my presentation. You also write similar codes and understand these things. Now, when you say, now we think about something called independent events. Here, these two events are dependent. Like when output is either greater than 3 or it is an even, the two are dependent actually. One outcome is, one event is dependent on the other event. Now, there are certain cases, certain events where they are not dependent. So, what is that condition? See here, suppose I throw a die and I toss a coin, say the die shows more than 2 and the coin shows head. But you know that these two are independent events. One does not depend on the other. I independently toss a die and a coin. So one event is the die showing more than 2 and the coin showing head, that is the second event. So this is they come together, that's a joint event, but the marginal probability of getting a head is 1 by 2 because getting a head is 1 by 2. Getting a marginal probability of getting output greater than 2 in the case of a die throw, that is greater than 2 means I have 3, 4, 5, 6, 4 possibilities are there. 4 by 6, that is a 2 by 3. Now these marginal probabilities are half and 2 by 3 respectively. Now what about the joint event? Joint event means the die should show more than 2 and the coin should show head. So those possibilities are this die showing 3 and H head showing 4, H, 5, H, 6, such. There are 4 possibilities. So then how many outcomes are in total possible? I have 2 outcomes for a coin and 6 outcomes for a die. So I have to have a total of 12 possibilities. So the marginal probability, the joint probability P A comma B will be 4 divided by 12, that is 1 by 3. Now we will demonstrate this by throwing this die and coin. Now that code is here. Here I have say I will toss a coin for say 1 million times. Okay, let us toss this by 1 million times. And this is my die, np.random.rand in 1, 7 size equal to n means I am throwing this die 1 million times. Now this is a coin toss. Y, what happens here is Y is actually a coin toss. Okay, so what I do is I create a random variable np.random.random. Okay, then I subtract 0.5. This is my threshold. Then I take the sign of this. Okay, so this may be a random number between this np.random.random gives me n random numbers in the range 0 and 1. Now when I subtract 0.5 from that, I get some random positive and negative values. When I take this sign, what happens is I get a plus or minus 1, random plus or minus 1. So to that array I will add a 1, so it will become an array of randomly spaced array of zeros and 2s, because when I add 1 with 1 it becomes a 2, when I add 1 with minus 1 it becomes a 0. So then I divide by I divide by 2 or I multiply by 0.5, so that this y will be a random array of zeros and ones. Okay, this you can test. Then like in the previous case, I initialize 3 sum values to 0, and then I create this joint event for I in range 0, n. If xi is greater than 2 and yi equal to 1, this simulates my joint event. That is, the die output should be greater than 3 and the coin should be a head. If xi is greater than 2 and yi equal to 1, outsum should be incremented by 1. So for every such joint occurrence, outsum will be incremented by 1. And here I have to check whether this marginal probability of xi die showing greater than 2. So I say outsum 2. If this is greater than 2, outsum 2 is outsum 2 plus 1. And if yi equal to 1, how many heads are there? That is outsum equal to 3 equal to outsum 3 plus 1. Then I compute these probabilities by outsum by dividing by n. Then I print out these probabilities, and let us run this code. This joined co-indi whatever. I will run this code join okay. Now here you can see that this joint probability P A comma B, this is nearly 1 by 3, 0.332903, and the probability of this this is 2 by 3 and this is 0.5. Now one thing is, this is my P A comma B and this is my P A and this is my P B. These two are marginal probabilities and this is a joint probability. Now here you can see that in this trial you can see that the joint probability is the product of these probabilities. I will multiply this 0.665967 with this value. I will copy this. that is not the one I am going to copy. I copy. Okay, here you can see that this product of this marginal probability, that is equal to the joint probability. So if the joint probability is a product of the marginal probabilities, then those events are independent. So let me go back to my presentation. So here you can observe that PA comma B, the joint probability, that is the product of the marginal probabilities PA into PP. So such events are called independent events. So for example, say look at that, maybe the apple imported in India and the number of people in mental asylum in India. They are independent things, they are quite independent things. So likewise, here you can see that this observation that PA comma B, the joint probability, if that is equal to the product of the marginal probabilities, if this is separable this way, then such events are called independent events. Now, this is another very important topic in probability, that is conditional probability. This plays a great deal of role in our signal reception and everything. So what happens is so far we have said about marginal probabilities and joint probabilities. They are probabilities based without any observation. So sometimes observation of an event may change the probability of another event. Okay, you observe some, you make some observations, that will alter the probability of another event. Okay. So for example, you want to receive some in your receiver, your transmitter is transmitting and the channel is corrupting that signal and the signal is received as a receiver. So if there is no received signal, the receiver has, if there is no received signal or corrupted copy received, then the receiver does not have any idea about the transmitted signal. So that probability of reception of getting a correct thing is very small. Then it observes the noisy signal. So based on that observation, the probability of getting a correct transmitted signal correct becomes increased. So for example, let us consider A and B are two horses in a race. A was constantly winning for a week. See, in a horse race, people bet on these horses. So what happens is I have two horses. This horse A was constantly winning for a week. So naturally, you bet on A. Okay, next 2 weeks, for the next 2 weeks race, you may bet on A. Then, but you get some other data that you get the data that B always won on a wet track. Okay, horse B was very good at running on a wet track. Okay, it is much better than A in wet tracks. And there is a weather report that there will be rains next week. Okay. So you get a weather report that there will be rains in the next week. So you will be tend to now you will change your decision. Instead of betting on A, you are likely to bet on B, because the probability of B winning now has been altered. Okay, so such data alter your betting pattern, and likewise in your receiver, what happens is if you don't have any received signal, then you have a total ambiguity about the transmitted signal. So as you get your data in, as you get your observation of the received corrupted copy of the corrupted copy in your receiver, you have a better idea about the transmitted signal. So based on this observation, conditioned by this observation, the probability is now changed. See, the conditional probability of an event A, given that another event has occurred. You have observed another event. So based on that observation, the probability of occurrence of A has been changed. Now that is changed as P A given B. A given B means you are trying to understand the probability of A based on the observation of the event B. Okay. So you are trying to estimate your transmitted signal based on the received signal, received corrupted copy of the signal. Likewise, here in that case, A is your transmitted signal and B is your received corrupted copy. So based on this corrupted copy, you estimate this A. So this P A given B, that is equal to the joint probability of A and B, that is P, the joint probability, this is a joint event A, B, probability of A comma B divided by PP. This PB is a marginal probability of B. Okay, so if I cross multiply this equation, you have PA comma B, that is equal to PA given B into PB. Okay, Now there is an interesting thing. This joint event, it is the same. Probability of the joint event is the same. It doesn't matter whether it is PA comma B or PB comma A. PA comma B is the same as PB comma A. You can remember, you remember that Venn diagram showing the intersection between the two events A and B. That intersection is the same. So PA comma B is the same as PB comma A. So what is PB comma A? If I change these variables, you can see that it is PB given A into PA. Okay, PB given A. This is PA given B. This is PB given A. Now you must understand that PA given B is not the same as PB given A. There are two things. But PA comma B is the same as PB comma A. But PA given B is not the same as PB given A. So what happens is, if I substitute this equation in equation 1, what will happen? PA given B, that becomes a PB given A into PA divided by PB. So PA given B, this A is the unknown quantity, B is your observation. PA given B, that's equal to PB given A into PA divided by PB. This looks like a school book equation, and this Bayes theorem is one of the very deep results in mathematics. It is very hard to compute this. Many people may say that they understood Bayes theorem, either they are telling a lie or they do not understand, they do not know what they are talking about. This is a theorem of great impact. So this term should be carefully understood. So I will come to that. This PA given B, so this is what is A, this is, as far as our communication systems are concerned, this is the thing to be got, A, that is a transmitted signal. This B is a noisy version, noisy observation. So this PA given B, this computation of this posterior probability is a very great challenge. There is a separate area called probabilistic programming. So computing this posterior probability is a very heavy task. So this PA given B, that is called the posterior probability. Okay, PA given B is called the posterior probability, and this PB given A, this PB given A is called the likelihood function. Okay, PB given A is called the likelihood function, and this PA, that's also an unknown quantity, that is called a prior. Okay, there's a prior information, that is your uncertainty about A without any observation of B. Okay, PA given B is the posterior probability. Posterior means after what? Prior means before that. Posterior means after something. After what? After observing B. After observing the corrupted copy. This is the probability. So PA given B will be a modified version of PA after the observation of B. So PA given B is a posterior probability. PB given A is the likelihood function, and PA is the prior. This prior actually reflects the knowledge of A without observing B. Sometimes what happens is, in real computation, this A is your transmitted signal. Sometimes you don't have any idea about the prior. So what happens if you don't have any idea about something? What people do is, there is something called principle of insufficient reason. Something called a principle of insufficient reason. So if you don't know about something, the safest way is to assign equal probability to every unknown thing. So what happens is, you can start with a flat or a uniform prior. Okay, these are basically, these will be probability density function. I will tell you what probability density functions are in the coming classes. So this may be probability density function. So this PA will be the prior. Initially you assign it to be a constant 1 or a uniform 1. So based on this known prior, this assumed prior or flat prior, you can compute a posterior distribution. Then what happens is, in the next iteration, that is, in the next iteration means when the new data set comes, or when new observation B comes, what you can do is, you can replace this prior with the old posterior. So the old prior, that becomes a new posterior. Okay, then you compute the new posterior. Again you compute this PA given B based on the new prior. So that you get a better understanding of A. What will happen is, you will get a better distribution for A. So that again you can use it as a prior and keep on computing until you get your desired signal. And what happens is the likelihood, this likelihood function, this PB given A is the likelihood function. So this is how, this function is how we will introduce data or observation in our analysis. It's an expression of the plausibility of the data given parameter. So how correct that noisy copy is, or noisy version is there, or noisy observation is there, given the parameters, what is, how plausible is the data coming in. So that is decided by the likelihood. Then the posterior distribution is a result of the Bayesian analysis and reflects all we know about a problem. So this is what we are ultimately trying to compute. What is probability of the transmitted signal given the noisy reception? Okay. So this Bayesian is actually a balance between the prior and the likelihood. Only if this prior and likelihood are strong, then only the posterior will be correct. So then there's a joke, there's an old joke saying that a Bayesian is one who, vaguely expecting a horse, on catching a glimpse of a donkey, strongly believes that he has seen a mule. Okay, this summarizes the dilemma in the Bayesian analysis. You are expecting a horse. What is a horse here? It is a transmitted signal. We do not know what that is. Okay, we haven't seen this horse before. But I know something is there. I'm expecting a horse. Then what is? I got a glimpse of a donkey. I saw the tail of a donkey. Okay. So that, what is that donkey in our case? That is the noisy received signal, the corrupted copy of the transmitted signal. That is my observation. So I caught a glimpse of a donkey. Then I strongly believe that I have seen a mule. Okay, not a horse but a mule. So this summarizes my problem. So if my observation and my likelihood are strong, then I can strongly say that I have seen a mule. Okay, so the meaning of this is, if the prior and likelihood are weak, that is, these two functions are weak, this is my likelihood and this is my prior, PA is my prior and PB given A, that is my likelihood. If they are weak, then I have a weak belief about my posterior. Okay. So then there is a term, the one we didn't discuss, that is this PB. This term is of no consequence, this PB. This actually, in our case, this basically the probability of our received signal, the received corrupted copy, or probability of the observation. There is nothing very fanciful about it. Even if I miss that term, nothing will happen. That function is called, that part is called marginal likelihood or evidence. PB is called the marginal likelihood or evidence. It is simply the probability of the observations act. This acts like just as a normalizing factor, nothing more. So Bayes' theorem can be written as PA given B, that is proportional to PB given A into PA. This term is called this PA given B, that's called the posterior probability, and this is my likelihood. PB given A, that's my likelihood, and PA, this is my prior. This is my prior. So I hope you understood these terms, and you understand the depth of the conditional probability and Bayes' theorem. There are many Python tools available for computation of the posterior probability. So in higher semesters, when you do more involved computation, you will come across these. So when I come to the end of the session, what you learned, or you reviewed joint events and independent events, and you observed the demos of joint and independent events. So independent events means P A comma B, the joint event, probability of the joint event, that is equal to the product of the marginal probabilities P A into P B. Then you understood the conditional probability. Then you understood the Bayes' theorem and learned the terms as posterior, prior and likelihood functions. And that is the end of this session. I thank you all.